In the previous module, we have looked at a specific domain restriction, which is the single peak preferences, where all the alternatives have a common ordering, which we assume to be on the real line, and there we can potentially circumvent the Gibber-Sadowitz theorem. And one of the examples were to set the temperature of a room, where we can either pick the median of all the temperatures, temperatures that are the most favorite temperatures of all the agents, or we can pick the coldest temperature, we can pick the hottest temperature. All these things are strategy proof. We have argued that in the previous module. In particular, you can see in a very similar way, the kth coldest temperature in the room, where k is a fixed number, is actually a valid social choice function, which is strategy proof in this setting. So you can say that I am not going to set the temperature as the coldest. We can set the temperature to be the second coldest, or maybe not the highest and the hottest, the second hottest. And all those things will be strategy proof in a very similar way that we have argued in the last time. So here we are going to define a social choice function which takes care of all such outcomes. So we will call this social choice function f to be a median voter social choice function if there exist some peaks. So b, which are, and there are n-1 peaks, we are going to call this peaks as the phantom peaks and the corresponding voters as phantom voters. I'll come back to this point, why do we call them. And the social choice outcome is the median of the real peaks, the peaks of these agents, and also the peaks of those phantom voters. If that holds, then we are going to call this social choice function to be the median voter social choice function. Now, what is the reason that we have used these phantom voters? Because in that case, by changing the phantom voters appropriately, we can consider all possible cases, the hottest temperature, the coldest temperature, or any kth coldest temperature as well. So for instance, if we want to have the social choice function which picks the leftmost alternative or the coldest temperature, then we can pick all these phantom peaks to be the YL, which is the leftmost point. So if I have the maximum and the minimum, so this is the lowest and this is the highest, then we can pick all these n-1s as YLs, and then the median of all those n-1 picks and augmented with the n voter picks, the median will always be the smallest of all the agent picks. So this automatically takes care of the social choice function which picks the coldest temperature in the room. Similarly, if you want to pick the hottest temperature, you can pick all these phantom picks to be the YH, and therefore the median is going to be the hottest temperature right after that. So that is the reason we have picked this phantom voters, which actually generalizes the all possible social choice functions in this space, all those things which are strategy proof. Now it's not very difficult to follow this result given the discussion that we already had, that every median voter social choice function is strategy proof, and the argument goes in a very similar way. You start with an FP which is the A, and if a player has A as this pick, then it has no reason to deviate. If it is on the left of A, then also it does not have any benefit misreporting, because the only way it can change the outcome is to move its pick to the right of A. And that is strictly worse a preference, worse an alternative than the current outcome in its own preference profile. Now you can immediately see that you can experiment with other kind of statistics. Instead of median, you can look at mean, and they do not have this property. You can verify that. You can construct examples where it can be manipulated. Mean is very easily manipulable. So now we are going to prove a kind of a characterization result about this median voter social choice function. For that, we need to prove certain intermediate results. And one of these intermediate results is the claim that suppose we have this P min and the P max are the leftmost and rightmost peaks of of this preference profile. When the players submit a preference profile P, find out what is the minimum peak, that is P min, and the maximum of that is the P max. And that is so this ordering is with respect to that natural ordering over these alternatives. Then if this social choice function is Pareto efficient, then it must imply and implied by the fact that it is lying within here. So the social choice outcome cannot pick something outside this P min and P max interval. It has to live somewhere in between. So that is the requirement for Pareto efficiency. The proof is really very simple. So suppose, so the forward direction we have Pareto efficiency will show that this must exist here. So in the forward direction, suppose that this does not hold, the right hand implication is not true. So therefore it is either below F min, so either it is the social choice outcome is below P min, then every agent prefers P min because that is the minimum alternative, and because of the property of single peakness, everyone's peak is above that. So they prefer P min at least as much as the outcome that we have picked, and therefore FP is dominated, and that cannot be a Pareto efficient outcome. And you can argue in a very similar way that if FP is greater than P max, then also a very similar thing happens. So now let us look at the other direction, that is, if we are given this is within that should be a Pareto efficient outcome. Now we can see here that the condition that because it is within P min and P max, it can never happen that there exists a single alternative, let's say an alternative B, which is strictly preferred than that outcome. So imagine what is happening here. So we have P max here and we have P min here. So all the peaks, so there exist one or more players whose peaks are here, but for all the other players the peaks are somewhere in between. You cannot really find one specific alternative, let's say, which was possible to find in the previous case, which dominates this outcome for all the players. Right? So this domination is not possible. If this Pareto domination is not possible, then the condition, the if condition of this Pareto efficiency is satisfied vacuously, and therefore this social choice function f of p is going to be Pareto efficient. Now we'll have to prove some of the results that we have seen for the domain which was unrestricted before we brought in the single peakness. But this needs to be proved afresh because those results were proved using certain constructions, and we'll have to be careful that those constructions are also carried forward in the context of single peakness. In particular, so what can happen? So here we can see one result which was true even for the in the general domain, the unrestricted domain, which says that if you have a social choice function which is strategy proof, it must be monotone. We have seen this result, but for that we have constructed certain things like we pick some alternatives A, B on top, and then right below this there was another alternative A, and we could have done this for arbitrarily for any preference for any alternative, any B or A. Now in the single peak domain, if you, let's say you have A on the left and there are and B is somewhere in between. So let's say so this is the P max, there is some P min, and there is A and B, but in between there are several other alternatives, let's say C, D, E and others. Now there could be an alternative where B is preferred over A, but then that means that all the C, D and E should follow a particular pattern. So I cannot really have, so if this is the case, I cannot really construct another preference. So if this ordering is like this, I cannot really construct a preference which has B right above A and there is nothing in between, because then it will not be, so this particular preference does not live in this single peak domain, because I cannot have B on top and A right below it, because then what will happen to the C, D and E? We will have multiple peaks if that happens, and that is not feasible here. So whenever we are doing some construction in this context, in the single peak domain, we'll have to take care of the fact that there are other alternatives also which are between A and B, and if we have to lift certain alternatives, we'll have to maintain the single peakness there as well. So this direction is easy to prove. You can actually check the same proof that we have used for single peak to implying monotonicity also holds in this context. But for the reverse direction, from monotonicity to strategy proof, I leave that as an exercise. You will have to carefully construct the preferences, or you can also provide a counter example. Maybe monotonicity does not imply strategy proofness in single peak domain. We have also seen this result in the context of the complete domain, that if we have a strategy proof social choice function, then these three statements are equivalent. Now we know that by the definition of it, the Pareto efficiency implies unanimity, unanimity implies ontoness. So this direction, this implication, sorry, the other implication direction, this is obvious by definition. What we actually need to show this equivalence is that ontoness implies Pareto efficiency when F is a strategy proof. And now we'll have to do it carefully, because this proof also requires some construction. We'll have to ensure that this construction, the preference profiles, live in the single peak domain. So let us assume for contradiction, so we'll have to prove this. We assume that F is strategy proof and onto, but it is not Pareto efficient. Then what does it mean? The not Pareto efficient means that there exists a pair of alternatives A comma B such that A is strictly preferred over B for all the players, yet the social choice outcome picks that Pareto dominated alternative B. So here is the point. So A and B could be far apart, so something like this, and there might be several other alternatives like this which are falling in between. So if you look at the previous construction, we have just picked some preferences where A was right below, B was right below A, and that was possible to construct because the domain was unrestricted. But because the discussion that we just had, we cannot construct that in a single peak domain. So we'll have to do the following changes. So there must exist another. So if this is a single peak domain, if A is preferred over B, then all these intermediate preferences have a very specific order. So that is, all these alternatives will lie in the same preference order as shown in this figure. So there must exist some alternatives C, which is a neighbor of B, which is just on the left hand side in this case. This is a neighbor of B such that C is strictly preferred over B, and this is possible only when we have a single peak preference. Of course, C can be A itself if there is no other alternative. Maybe A and B are sitting next to each other, then A becomes that neighbor here. But nevertheless, we can always find a C which could be different from A itself. Now we apply the property of ontoness, right? So we are going to prove that this social choice function is strategy proof and onto. So ontoness says that there must exist some P prime, some preference profile for which the social choice outcome is C. Fine. Now we are going to construct P double prime, and we will construct P double prime in the way such that P double prime lives in the single peak domain. So so instead of picking A to be on the top, we are picking this alternative C to be top, because C and B are adjacent to each other. Now for all the players, we can actually pick C to be on the top and B to be the second highest, right? So this can be done for all the players. This can live in the single peak domain itself. Now here is the contradiction. So if we go from P to P double prime, note that in P the outcome was B, that was by assumption. C is also above P, so B is Pareto dominated by C as well. Then by monotonicity we can conclude that f of P double prime should be equal to B for this transition. but in P prime we see that the outcome is C, right, which is different from B. And what we have done in P double prime is that we have pushed C to the top for all the players. So of course, using monotonicity, we can find that P double prime is equal to C, and this is a contradiction. So we have actually emulated the same proof that we have done for the unrestricted domain, but the construction that we have done, P double prime, is slightly different, and that is required because we are in a single peak domain. Now, one of the reasons why we came from the complete domain, the unrestricted domain, to this restricted domain of single peakness is because we are interested in non-dictatorial social choice functions. We know that by Gibber's-Adelbert result that we can always have dictatorship in the complete domain. Here, of course, the dictatorship will still continue to be a strategy proof, but if we restrict such that this the social choice function becomes non-dictatorial, and then we can and we have already seen there exist some examples, some social choice functions which are non-dictatorial. So how can we characterize them? How can we put more properties such that non-dictatorships, the dictatorial social choice functions are ruled out? So one such property is called anonymity. In simple words, you can say that the outcome is actually insensitive to agent identities. So no matter whether player 1 or player 2 had this preference, if collectively the people have the same preference profile, then the outcome should not change. So let us state this property anonymity a little more formally. So let us assume that there exists a mapping sigma which maps player set into the same player set with a possible renaming. So let's say sigma of player 1 now becomes 2. So that is, in the original game, if it was player 1, now in the modified game the player is player 2. And this is a valid permutation. That means it's essentially a bijection. You cannot have two players mapping onto the same player. Now, using this property of this permutation function, we can apply this permutation function sigma to a profile. So a profile, preference profile capital P, to construct another profile where the preference of player I in the original one, so let's say in this case the preference P1, so let's say P1 now becomes the preference of P2, player 2's preference in the modified game. Now we are going to denote that preference with the superscript P of sigma. So let us look at an example to understand this point. So suppose we have 3 players, and sigma is the following. It maps player 1 to 2, player 2 to 3, and player 3 to 1. Now what is the meaning of P? So this is the original P, and this is the modified P sigma. So what is happening here is that the preference, so player 1's preference is here, and in the modified game player 1 has become player 2. So player 2 now has this preference ordering. And similarly, if player 3 has become player 1 in the modified game, its preferences, its ordering has become the same as player 3 in the original game, and similarly for player 3 in the modified game. Right? So that becomes the preference of player 2 here. Now, what does anonymity say? And the social outcome. So if Fp was something, the Fp here will also become the same. So sigma should be equal to f of p. That is the requirement of anonymity. Just because you have relabeled the players, it should not change the outcome. That is anonymity. So it says that a social choice function is anonymous. We will use this shorthand anon for this, if for every preference profile P and for every permutation of this agent sigma. So this is important, that it is not true for one specific sigma, it is true for any possible sigma. The outcome does not change, then we are going to call that this is an anonymous social choice function. Now you can clearly see what this brings in. So can you think of a non-anonymous social choice function? And we have already discussed it before. So what can be an example of a non-anonymous social choice function? Yes, perhaps you have guessed it right. This is dictatorship. We know that dictatorship picks a specific dictator. So let's say dictator is a specific player D, and we know that the preference of that player, the topmost preference, is always going to be the outcome of this dictatorial social choice function. Now, once you change the dictator, so if you permute the player orderings, then a new player becomes a dictator. That player may also have a different alternative. So player one in the first preference, let's say if here we were going to pick the topmost alternative of player one, here the topmost alternative of player one is different. So they are not following these anonymous rules. So therefore, dictatorship is an example which is non-anonymous. So by restricting to our attention to only anonymous social choice functions, we can rule out dictatorship. And we'll see that the median voting rule is actually anonymous, because the median only looks at the picks, and based on their ordering on this real line, you pick the median, and the median is insensitive of who is the median voter. As long as the set of the picks are the same, the outcome should always remain the same. So therefore, median survives, but dictatorship does not survive when we additionally apply this property of anonymity.